Doing okay this morning? Yeah. We just have a couple days left. We are going to have a quiz on Thursday. If you don't want to take it, that's fine. You don't have to take it. But I'll let you know. It's going to cover that next chapter on nuclear radiation. And not the entire chapter. I'll let you know. Probably up to, I'll let you know at the end of class. They're not, no. But I'll be, as we go through the notes, I'll try to be clear. You need to know the different nuclear reactions. We're going to do some practice problems in class. All right, the different types of particles that are formed. If we get into health applications, you'll need to know some stuff about that. But I'll be clear about what you need to know. Okay? Trust me? No. It's on Thursday, yeah. Tuesday, yeah, which you'll submit it online. I'll put the Moodle thing up today. I just put a note to myself. I'm sorry I haven't done that yet. I know some of you are ready to turn it in. Absolutely. So if you want to email me your paper beforehand, just give me a few days, a couple of days at least, and I'll tell you if there are any issues or if this is an A paper. Okay? So just give yourselves a couple of days. That's fine. It helps me too, so then I can get some early grading done. Yes, Deja? The last day of class, which is Tuesday, a week from today. Huh? Yeah. But if you're doing a presentation, I know there are a handful of you that are doing presentations. You're going to do that on Tuesday at the rec center. Okay? No, we'll meet at the rec center. There's a classroom upstairs. You know where the classroom is upstairs? Okay, it's upstairs. You go upstairs. You go into like above. Like when you walk into the building, you look up and you see, the open area. It's up in that on one of those balconies. As you walk in, it's on the right. Just ask the people at the front if you're not sure, or just walk around upstairs. It's not that big upstairs. Okay, and then we'll be in there for a little bit, and we'll do our presentations for about 20, 25 minutes, and then we'll go around and look at some various things in the rec center. Okay. It'll probably take most of the time there, so try to plan accordingly. If you're in a rush to get to class, you need to leave early, just let me know, depending on where your class is. All right. Any other questions about stuff? The exam is on the day of our final. Not really it's not a final though. That exam is on the 10th of May at 8 a.m. It'll be in this room. It'll just be like the chapters that we haven't done. The one on nuclear radiation, the one on optics. I think that's all right. Just optics and nuclear radiation. The portion that we do in the next day and a half. Okay. You'll also take a general education assessment. It will be cumulative. So if you want to prepare for it, that's fine. If you want to just sort of go through your notes, sort of review the stuff that we've done. That'll be for extra credit. It'll count for up to 10 points of extra credit. You'll get whatever percentage you get on that assessment, you'll get an extra credit. Okay? If you want to review, that's fine. If not, that's fine too. Um, I think you'll probably do okay on it without reviewing. All right, let's get started. We're looking at the biological effects of nuclear radiation. We're actually probably just going to look at the different types of nuclear reactions that we have and the type of radiation that it produces. And then if we have time, we might get into sort of how radiation interacts with the body. Um, but first of all, let's just review the electromagnetic spectrum. You need to know this for the light chapter anyway, right? So our EM spectrum, just to remind you, when we're talking about radiation, we're usually talking about electromagnetic radiation, and that electromagnetic spectrum runs from the radio to the microwave, to the infrared, to the visible. Remember, within the visible, we have red, orange, yellow, green, blue, and violet. Um, and then beyond the visible, we have the UV, the X-rays, which we'll talk about, and gamma rays. So mostly in this section, we're talking about this, but we're also going to talk about radiation that's not really photons. These are all types of light. We'll also talk about different types of nuclear radiation that are particles. And usually when we say nuclear radiation, that's what we mean, is that we're discussing particles that are ejected from the nucleus when they are either unstable or they're, some type of reaction is going on. But we will discuss gamma rays and X-rays, which will result from some of these reactions that we'll deal with. Not all radiation is harmful, obviously. Right. Gamma rays and X-rays or at least X-rays over a long period of time can be damaging. Gamma rays can damage your body. Usually, if you have ionizing radiation, it is harmful. Uh, Ionizing radiation is usually harmful. And ionizing radiation, when I say that, you have a cell in your body, there's a nucleus, there are electrons around it, and an ionizing radiation is some particle or photon that comes in, and there's an electron here, kicks it out. So it makes that atom or molecule into an ion, and that can be damaging to your body. Okay? Let's watch a video. This is it's just sort of for fun, but it's Veritasium, and it's about radiation and the effects of radiation. Um, College, and she did one of her senior projects on measuring the radioactivity of bananas. And she, first of all, she had to set up this little lead structure. So she took these lead bricks and set up this lead structure, and she put her detector inside of that. And the lead structure was just to keep other radioactive radiation from coming in and giving her some background noise. Because as he said, there's radiation all around us at low levels. And then she took a bunch of bananas and she mushed them all up and put them into a bag and just like, I don't know, a couple dozen bananas and put them into a Ziploc bag and wrapped them all around the detector. And then we went away for spring break. You know what happened? What happens to bananas when you leave them out? They what? Yeah, they turn around and they decompose, right? And when they decompose, they give off gases. And so the Ziploc bag that she had sealed up started expanding and expanding, and then it blew all these lead bricks off the table, and just nasty banana all over the lab when we got back after a week. It was pretty gross. But she did actually detect a signal from the bananas because they do give off a certain amount of radiation. They have a what now? No, we didn't really have video cameras back then. I mean, not in the, I mean, we did, but not like a cell phone with us all the time. Um, okay, so let's see. Ionizing radiation is usually harmful. Um, as he said, microwaves and radio waves, they are not ionizing just because they don't have enough energy to cause electrons to eject from an atom. Right? They're very low energy, whereas gamma rays and X-rays, they are ionizing and they can be damaging. And then also, which we'll talk about today, are alpha particles. Uh, the Greek letter alpha is this, so we'll talk about alpha particles and then also beta particles. The Greek letter beta looks sort of like a B. Both of these are radiation, but they're not electromagnetic radiation. These are actually particles, usually traveling at a very high speed. So they have lots of energy. Right, remember our kinetic energy, 1/2 mv squared. Uh, if you have a high speed, then you'll have a lot of kinetic energy. And alpha and beta particles both occur in or in nuclear reactions. When I have an unstable isotope that changes into a more stable isotope. Let's first talk about the nucleus. You've probably seen this before, but you will have some questions on the next test just about the nucleus and the models that we have of the nucleus. Sure. What is it, Carly? What are you trying to read? Yeah, that's a K. For kinetic energy. Yes. So the kinetic energy of these particles, since they're traveling at high speeds, they have a lot of energy. And they can be ionizing. They can cause damage. Okay? All right. So in the nucleus, there are atoms. This is like third grade stuff, but you know, atoms have protons, neutrons, and electrons, or have uh, protons, neutrons, and electrons. There's also sort of this whole soup of material that we'll talk about, different types of particles, but primarily we have protons, neutrons, and electrons. Um, Protons are positive, neutrons, right, neut means they're neutral, so they have no charge at all, and then electrons are negatively charged. Protons have a big mass, electrons have a small mass, and then neutrons also have a big mass, which is going to be the same as our proton. So a neutron is like a proton, except it's neutral. Um, we have a bunch of different models that have come out over the years, just in the last century. In 1909 was the planetary model of the atom. We still use these in various ways because they're all correct in one way or another. There are some models, of course, that are just not correct at all, and I'll mention one of those. But in the planetary model, electrons orbit the nucleus like planets around the sun. This was pretty big deal because it replaced a model that is sort of held all throughout the 19th century called the plum pudding model. You ever had plum pudding? I haven't either. But prior to the planetary model, the plum pudding model said that you basically just have this bunch of particles that are just sort of all oozing around one another, like plums and pudding, or like raisins and pudding. And so this was in contrast to the plum pudding model, which had no distinct nucleus. Even with the plum pudding model, they knew that there were positive and negative charges, but in the plum pudding model, they just imagined that you sort of had this space and you had positive and negative charges that just sort of all lived together and just sort of mingled amongst one another. There are variations of the plum pudding model. This, by the way, was in the 19th century, in the 1800s. So in the century preceding the planetary model. With the planetary model, what you had was a nucleus that was positively charged, and then there were electrons that orbited around just like in our solar system. Right, that's why it's called the planetary model. They would orbit in different types of orbits, so you might see it like that, or you might see the planetary model where you have these orbits that sort of go around like this. That's sort of like, what's that show? They have a picture like that. Big Bang Theory, right. So that's called the planetary model. So next time if you're watching the Big Bang Theory with your friends, you could say when that picture comes up, you could say, hey, that's a much better model of the atom than the plum pudding model. And then you can bring out your plum pudding and y'all can eat plum pudding. You can talk about all the different models of the atom over history. Um, there's another model that came about sort of, gosh, I think it was like the mid 19th century called the shell model. They're still used today. The shell model um, says that electrons inhabit particular shells around the nucleus. These shells are discrete. So they don't come together, they're separated, they're discrete. And electrons can't be in between shells. They're either in a shell or they're not in a shell. So if I were to look at a model, this is going to look a lot like the planetary model, but it's a little bit different, where I have these shells that are predefined, and the electron can only be in one of these shells. So the electron can be here, or an electron can be here, or an electron can be here, but it can't be in between. I can't have an electron in between shells. This is probably the one that you learned in high school, I'm sure, or chemistry or whatever. So the shell model is something that we use today, that electrons can jump from one shell to another. They can either go down or they can go up, but they can't go in between shells. Let's see, I want to show you, let's go back for just a second. I want to show you a little model of the planetary model. The planetary model is the Rutherford model. Let's see, here's this is an animation of it. So this just shows the electrons as they go around in different orbits around the nucleus. The nucleus in the middle is positively charged, and you have these electrons that sort of zoom around it. I think there's a picture of the plum pudding model. Um, no, I don't see it. Okay. Anyway, so the shell model, I have these distinct shells that exist. Um, we're going to be mostly concerned with the nucleus of the atom. In the nucleus is made up of nucleons. So in chemistry, right, you mainly are concerned with the electrons, what the electrons do. But in this chapter, we're mainly concerned with what happens within the nucleus. What happens when you change the number of protons or neutrons or a few other particles, positrons or electrons that are actually inside the nucleus. So this is different, even though some of the reactions that we'll show will look a lot like what you do in chemistry. Y'all had chemistry here at Nichols? Yeah, some of you know? Okay. But you had it in high school, right? Yeah. So anyway, our reactions will look a lot the same, but instead of talking about what happens to the electrons, we're talking about the particles in the nucleus. So the nucleus is made up of nucleons. Uh, these nucleons are protons and neutrons. It'll be very important for you to know the nomenclature that we'll use. The number of protons we're going to give as Z. So Z, the letter Z, capital Z, is the number of protons. As you know, I think you know, this tells us what is the atom. Is it a carbon atom? Is it a nitrogen atom? Is it oxygen? Is it uranium? Whatever. What type of atom this is given by the number of protons. Then I also need to know the number of, well, Z is the atomic number. So if I look at a periodic table, the number here, that's a terrible image. The numbers that are given here, those are the atomic number. They tell us how many protons I have. So my hydrogen has 1 proton, my helium has 2, lithium 3, beryllium 4. And the way you get to the next atom is you just add another proton. So down here, if I were to go up to 119 protons, then I would have a new element. And they can make new elements, but they're often unstable. They are unstable. As you get up to a certain size in the nucleus, that nucleus can just no longer maintain stability, can no longer exist for any lengthy period of time. All right, so Z is the number of protons. It's the atomic number. The charge of the nucleus is Q, and that's going to equal to plus Z, the number of protons, times our fundamental unit of charge. We've seen this before. E is equal to 1.6 times 10 to the minus 19 coulombs. You don't need to know that number. It's not going to come up on the test at all, but just know that that is a particular value. This is our fundamental unit of charge. It's the same charge on a proton and an electron, except the electron is just negative. So the charge of the nucleus is just Z times that value, because Z is the atomic number. Atoms typically have the same number of protons as neutrons. Go back to my periodic table. Let me get another one that has atomic mass on it. Okay, so for example here, uh, atoms don't have to have the same number of protons as neutrons, and we'll find actually that unstable atoms are usually those atoms that have more or fewer neutrons than they have protons. So if you have 5 protons and say 12 neutrons, then that's going to be an unstable nucleus, and it's not going to hang around for long. But here, if I look at my periodic table, this is my atomic number, and then this is my atomic mass. So there's some other things in here, but roughly I have my atomic mass, which here is about 10. I have my atomic number, which here is about 5. This tells me I have 5 protons, 5 neutrons. Okay, so I have 5 protons, and then I have in my atomic mass, which is including the protons and the neutrons, that I have 5 protons and 5 neutrons. So typically, in a stable element, I'll have the same number of protons as I have neutrons in that nucleus. Atoms that have the same number of protons, that's the same atomic number. Remember, that's the number of protons. Z is the number of protons. But different numbers of neutrons are called isotopes, or nuclear isotopes. Right? I'm sorry, nuclear isotopes. So, for example, looking back at my periodic table, let's say I have carbon. Carbon has, well, let's do one that's easier. Right, lithium, which has 3 protons. If I look at lithium, I can have different types of isotopes. Lithium has 3 protons. In a stable lithium atom, I'll also have 3 neutrons. But if I have, say, 3 protons, that's still lithium. That defines it as lithium. But if I have 4 neutrons, then that's going to be an isotope of lithium. And we'll see that with several different atoms when we look at their reactions. Isotopes are usually unstable. That means that they'll decay over time. Okay, let's look at the energy of the nucleus. Can I go down from here? Let's see. So let's just sort of go back and I'll give you some ideas sort of what type of questions to expect. Um, you'll see the EM spectrum, but we'll see that for the previous chapter anyway, just knowing the order of the EM spectrum, right, because we have that in the chapter on light. Um, knowing that ionizing radiation is harmful and what it means to be ionizing, that ionizing means that it can cause an electron to come out of that shell uh, of the atom. Needs to know about our protons, neutrons, and electrons, how they differ in charge and mass, and then the different models. The planetary model, just meaning that you have this distinct nucleus, which was a new idea at the time, and the electrons orbit around them like planets. And then the shell model, the idea being here that I have distinct shells. They are discrete. Electrons can be in a shell or in another shell, but they can't be in between shells. Okay? Um, and then also knowing that the nucleus is made up of just protons and neutrons. Remember, neutrons are positively charged, or excuse me, protons are positively charged, neutrons are neutral. And then this atomic number, I might even give you like a little piece of the periodic table and just ask you for scandium, what is the atomic number? And the atomic number would be 21, for example. Okay? Pretty basic stuff. I think you've probably seen a lot of this stuff before. All right. Let's get into a little bit that you might not have seen. The energy of the nucleus. Listen, it's really easy to remove an electron from the outer shells, especially of an atom, but it's not easy at all to remove, say, a proton or a neutron from the nucleus of an atom. So the reason is that is because it has higher energies, binding energies that bind it. So really easy to remove an electron. I use that symbol for an electron. It's the fundamental unit, the E, with a negative on it. So it's really easy to remove an electron because the energies involved are really low. We use a unit of energy when we talk about atomic physics. It's called the electron volt. You might have heard of the electron volt before. The electron volt is the amount of energy that an electron gains when it crosses across 1 volt of potential. So you remember a volt from a previous chapter is a energy per unit charge. That's our potential. Y'all remember volt? It was energy per charge or joule per coulomb. So you can imagine that if I multiply the energy, the charge of an electron times a volt, which is energy per charge, then I get just energy left over. So an electron volt, if I take an electron and I put it across 1 volt of potential, that's how much energy it will have in joules, is 1 electron volt. And for energies regarding electrons, removing an electron from an atom is, on the order of 10 electron volts. 10 to 20, just a handful of electron volts. Whereas um, when we're talking about taking a proton or a neutron from an atom, then we're talking about millions of electron volts. So for example, to remove an electron from a helium atom, or from a hydrogen atom, to remove an electron from hydrogen, this is like 13.6 electron volts. That might be a number that's familiar to you from chemistry. But to remove a proton or a neutron from, say, helium, I can't remove a proton from hydrogen, right? Because if I removed a proton, there would be nothing left. Hydrogen only has one proton. And it turns out that hydrogen doesn't have any neutrons either. So to remove a proton or a neutron from a helium atom is, gosh, what is it? It's like 7 million electron volts, 7 mega electron volts. So there's just a huge difference between these in removing an electron or changing an electron in an atom and changing a nucleus of an atom. Huge, millions, orders of magnitude different. Um, as a result of this, we're going to have a vast difference in the amount of energy available from nuclear processes to more traditional processes of energy production. Because most traditional processes of energy production, they involve manipulating the electrons. Burning coal, boiling water, all that business is a process that requires moving an electron from one state to another. That's where that energy comes from. So there's a vast difference in that. So for example, if I take, say, 100 grams of coal, I can get about a million joules out of that, about 10 to the 6 joules. But if I take 100 grams of uranium, which is radioactive, and I extract the energy from that by nuclear processes, not electronic processes, then 100 grams of uranium give me, gosh, like 10 to the 13th joules. So that's why nuclear energy can be so useful, just because there's so much energy that's wrapped up in the nuclei of these tiny little portions of material. Just 100 grams of uranium, like 10 to the 13th joules. All right. This energy difference comes about from the strong nuclear force. Remember, there were four fundamental forces. I don't know if y'all remember back. I guess it was back in like the second chapter, maybe even the first chapter. But there were four fundamental forces of nature. Do you remember any of them? I'm sure you do. But what's the first one? Like one of the first things that we think about when we have forces in nature. What are they? What's one of them? What? Right, gravitational force. Right, it's sort of the most ubiquitous that we encounter. So we have the gravitational force, and then a little bit later, not that long ago, just a couple chapters ago, what's another force that we encounter? What's it? Another force that we encounter? Okay, well, frictional force is a type of force, but it's not one of the four fundamental forces. So we have four fundamental forces, two of which we've dealt with in this class: the gravitational force and then wait, not everybody at once. The normal force is a result of the gravitational force. The electronic force. So those are fundamental forces. They're distinct. They come about from different things. The gravitational force and the electronic force, the force between two charges. But now we're also going to add two other forces. The strong nuclear force is a force between subatomic particles. It's not a gravitational force. It's different from that. But if you get these particles close enough to one another, then they begin to attract to one another. But they have to be really, really close, like on the order of the nucleus. So the strong nuclear force doesn't affect us because we're so far away. Okay? So we have the strong nuclear force, and then there's also something called the weak nuclear force, which we're not going to deal with at all. Let me just write those down. We have four fundamental forces. We have the gravitational force. We have the electronic force, or the electric force. Which one of these is bigger, by the way? The gravitational force or the electric force? Have any idea? Think the gravitational is? Yeah, I think that's what most people think. But the electric force is actually quite a lot larger. I mean, it sort of depends what you're talking about, but the electric force is larger typically than the gravitational force. And then the other two are the strong nuclear force. Right, because if I have protons in a nucleus, what's going to happen to those protons? Have you ever thought about why the protons in a nucleus are the way that they are? Because they're really close to one another. And if you remember from our electric force, F is equal to KQQ over R squared. If I make R really small, that means that the electric force between these protons in a nucleus is just huge. Have you ever thought about that? Why the protons are in a nucleus and why they're so close to one another? You haven't ever thought about that? Okay. Well, you should. I mean, in fact, it wasn't really terribly crazy for people to think of this plum pudding model because the plum pudding model, right, the protons are all spread out because they knew about electric forces. We know about electric forces. They would experience them in the lab and everyday life. And so they said there's no way for these protons to be all collected in the middle. That's crazy to think that these protons can be all jammed up right up next to one another because the electric forces on them are going to be so huge, they're just going to fly apart. Okay? So there is a really huge electric force acting in the nucleus, but it's the strong nuclear force that holds these together. The strong nuclear force is much, much larger than the electric force, which causes these nucleons, these protons, to all come together. And then you know what? The neutrons, which are also in here, they help because there's also a strong nuclear force between those. This strong nuclear force exists between objects of mass, but only over very small distances. So the strong nuclear force acts between objects of mass, but only over very small distances. All right, those distances are on the order of like 10 to the minus 15 meters, which is basically about the size of an a nucleus. In fact, if your nucleus gets much bigger than this, it becomes unstable and will emit radiation. So on your periodic table, basically everything bigger than lead is radioactive. It's unstable because the nucleus has gotten too big for the strong nuclear force to hold everything together. And those things will exist, but they decay over time. All right, let's look at nuclear notation. It's going to be sort of a big deal on your test that you know how to do nuclear notation because it'll be important that you know how to do the different reactions. And knowing nuclear, if you know the notation, then you'll know how to do the reactions. So let's look at nuclear notation, and then hopefully we'll get into a couple of reactions that'll help set you up well for the quiz. Oh, yes, thank you. The fourth is the weak nuclear force. We're not going to talk about it at all. It occurs, though, in some radioactive decay, not in all of them. But so this is 1, 2, 3, 4. You should know the four fundamental forces, be able to pick them out from a list, right? You don't make you write them, but be able to recognize them as one of the four fundamental forces. Also know that the strong nuclear force acts over small distances, and it also helps, or it holds those protons together, even though they have huge electric forces that are trying to push them apart from one another. The strong nuclear force is that much stronger than the electric force that it can hold it together. That's why, you know what? Why they called it the strong nuclear force. Wait, I don't know if you were wondering about that, but it's because it's so strong. It can hold those atoms together, the nuclei together. Okay, so let's look at nuclear notation. Your book does a pretty good job of describing this. Um, I have some chemical symbol. I have the atomic mass number, and I have the atomic number Z. So it'll be written like this. X is your chemical symbol. Is it hydrogen? Is it helium? Is it lithium? Whatever it is. I'll give you some examples. Uh, Z is what is Z? Do y'all remember? It's the atomic number. It's the number of protons, right? So this is the atomic number. And remember, it's the number of protons. And then A is the atomic mass. And this is the number of nucleons. So notice here that atomic number and atomic mass are related, right? Well, which one's going to be bigger, Z or A? The atomic mass or the atomic number? The atomic mass will usually be bigger, right? Because it includes not only the protons but also the neutrons. Although notice here, if I write the nuclear notation for hydrogen, I'm going to write 1, 1. What does that tell me about hydrogen? It has what? Okay, it is neutral. It is neutrally charged, but that has to do with the number of protons in the nucleus and the number of electrons. So actually, it may or may not be neutral. It depends, does it have that electron? But what does it tell us about the nucleus of this atom? What does it consist of? What does it consist of? Does it have a neutron is what I'm trying to get at. It does not have a neutron. It has one proton, and it has one nucleon. But these two are the same. It has one proton and one nucleon. Whereas let's say that I look at, say, carbon-12. I go back to my periodic table. Where's carbon? Right. Carbon here has 6 protons, and its atomic mass is 12. So I have the atomic mass here. I'm going to have the atomic number here. What does this tell us about the number of protons and number of neutrons in carbon? It has how many protons? How many protons? It has 6 protons, and it has 12 nucleons. So carbon-12 has 6 protons, and then it has 12 minus 6. That is A minus Z equals 6 neutrons. All right, so the atomic number tells us the number of protons. The atomic mass tells us the number of protons and neutrons. So if you want to know the number of neutrons, then you'll just take the difference in those two numbers. We're going to see that those numbers, just like you had in chemistry, they have to be conserved. Like you had, remember when you did chemical equations in chemistry? You had to conserve the equate, conserve whatever. You're going to have to do the same here. That the number of nucleons will be conserved, and the number of protons on each side will be conserved. Often, this bottom number is left off. I won't do that, but often, instead of just seeing carbon-12, 6, you'll just see carbon-12. They will leave off Z, because Z is really defined by what is the element. Or Z defines the element. So somebody will look at carbon-12 and they say, well, of course it has 6 protons because it's carbon, right? Carbon has 6 protons. Okay, so that's atomic notation. Also, just want to remind you that for for our various particles, say protons, Z will equal +1. For electrons, Z will equal -1. We'll talk about electrons not in the sense of orbiting electrons, but we'll see in particular cases the nucleus can grab electrons from the orbitals and actually combine those electrons with protons to make neutrons. It's called electron capture. So we'll see that. So we'll deal with electrons, but not in the way that you do in chemistry. Neutrons, Z will equal to 0. And gamma rays Z is equal to 0. So we're going to use atomic number to denote the charge of things as well. Atomic number, remember, is Z to denote the charge. Alrighty? Let's look at isotopes, and then we'll start doing some different decay things. Let me go to the next page. It's a section called Isotopes and Stability. I already mentioned this, but isotopes have the same isotopes of an atom. Have the same number of protons but differing numbers of neutrons. So isotopes of an atom, they have the same number of protons. The number of protons defines what is the atom. Hydrogen atom has 1 proton. A helium atom has 2 protons. If you add a proton to your helium atom, it gets 3 protons. It's no longer helium. It's now going to be lithium, right? So they have the same number of protons. That means that isotopes have the same what? The same A or the same Z? If they have the same number of protons. Same A or Z? It is the same Z. That's our atomic number, which is the number of protons. But because they have differing numbers of neutrons, they have different values for A. They have different atomic masses, right? So, for example, with carbon, I can have a bunch of different isotopes of carbon. I can have carbon-8. That's the smallest isotope of carbon. How many neutrons does carbon-8 have? Oh, let me rewrite it actually. So carbon-8 looks like this. How many neutrons does carbon-8 have? Not 4. It has 2. Right. Normally on the test I would write it as carbon-8, 6, like that. Right, the 6 is implied for carbon because carbon has 6 protons. It has 8 nucleons, so it has 6 protons and 2 neutrons. So carbon-8 has 2 neutrons. That's 8 minus 6 equals 2. But you can have other isotopes of carbon. You can have 8, you can have 9, which would have 3 neutrons. You can have 10, you can have 11, you can have 12. 12 is the most stable form, right? 6 protons, 6 neutrons. Typically, same number of protons and neutrons are the most stable form for an atom. But I can have 13, 14, all the way up to carbon 22. So like for example here with carbon 22, I still have 6 protons. I got a whole bunch of neutrons. I got 22 minus 6. What's that? 16. 16 neutrons. All right, so you can have a lot of different isotopes. It's not the same for all atoms. Some atoms have isotopes that are just so unstable that they just don't really exist in nature. Okay? And some are just physically impossible to have. But for carbon, you can have anywhere from 8 up to 22. You don't need to know that, but you do need to know how to, that if I have differing number of neutrons, that's still the same type of atom. It's just an isotope of that atom. And then also that if I have equal numbers of protons and neutrons, then that's typically a stable nucleus. All right. Um, we can have isotopes of hydrogen. There are only 3 isotopes of hydrogen. You might have heard of these. You have H1, H2, and H3. Why don't you take a minute and just try to write the nuclear notation for these 3 isotopes of hydrogen, H1, H2, and H3. That is, so for example, with H1, we've already written this one, but it has 1 proton, and it has 1 nucleon. So try writing the nuclear notation for H2, that's called deuterium, and H3, which is tritium, which you may have heard of. H2 is deuterium, H3 is tritium. All right, H2, what is it? What's on the top? 2, and on the bottom? 1. And H3 on the top? 3, and on the bottom? 1. H2 is called deuterium. Sometimes it's called heavy, or when you have deuterated water, that is when you have water, H2O, but it's made with deuterium. You ever heard of this? Deuterated water. That's sometimes called heavy water because it has extra neutrons in there. Tritium is radioactive. Um, I used to work at Los Alamos when I was undergrad, and in Los Alamos, they did a lot of nuclear testing back in the 40s and 50s, right? And as a result, some of their groundwater uh, has been contaminated with radioactive waste, in particular tritium. And tritium is very difficult to clean out because it basically bonds to the water, and you can't get rid of it. You just can't get rid of it. So the tritium, actually, they use to trace out the groundwater around Los Alamos, which is pretty cool. Because, out in the Southwest, groundwater is pretty important because there's not that much of it. And they'll use detectors to measure where the water goes just by measuring the radioactivity of the water. I thought that was very interesting. Did y'all know that? Yeah. So anyway, those are your isotopes of hydrogen. You can have different isotopes for almost all the atoms. Um, all right, so you go back to sort of chemistry. Molecules and atoms become unstable because of the electron configuration. All right, so if I have my nucleus here, I have these shells, like in the shell model. Gosh, how many electrons are in the first shell? I always forget. I think there are 2. Is that right? Are there 2 possible electrons in the bottom shell? You don't know? Like if I just make up a number, we say, yeah, that's fine. Okay, is it 2? What's in the next shell? Is it 6 or 8 or 4? I don't know. We'll just say there's 4. Anyway, in each shell, there are a particular number of electrons. And when you have that number of electrons, it's considered full, right? That shell is full. So if, say for example, I have a shell that's missing an electron, Did y'all figure it out? What is it? 6 or something like that. Yeah, I think you're right. So anyway, doesn't matter how many there are. But the point is that you have a set number of electrons in each shell. And if you're missing one, like right here, I got this big gaping hole with no electron, then what's going to happen is you'll get an electron that will go down and form this more stable configuration. Right? So when molecules and atoms, that's what happens, that you get this more stable configuration. This is not so with nuclei. Not exactly the same anyway. By the way, when this electron moves from a higher energy level to a lower energy level, what's it going to do? Any idea? It emits a photon. And also, so here I emit a photon. When I have an electron that moves from a lower energy level to a higher energy level, that's because a photon has entered the atom and it's absorbed a photon. This was what was predicted by the shell model of light, that or the shell model of the atom. That I have these distinct shells, it requires a photon to move between shells. When they move to lower energy levels, they emit a photon that's equal to the energy difference between those levels. When I move from a higher to a lower energy level, excuse me, from a lower to a higher energy level, it's because the atom has absorbed a photon. Jogging your memory from chemistry? I should have covered this in chemistry. Yeah? No? Sorta? Alright. You need to know what the shell model is. And you do need to know this basic idea that we have these distinct shells where electrons fill them, and they require a certain amount of energy to go in between those shells. So not so with nuclei. When nuclei become unstable, it emits radiation. So an unstable nucleus will emit radiation. Uh, and enter a more stable configuration. And I mentioned this before, but usually unstable nuclei are unstable because they're too big. Because remember, if I have my nuclei, I have all these protons. Let's just forget about the neutrons, but they're there. I have all these protons that are jammed in here together. They all have positive charges. They're really close, so they have electric forces acting upon them. Say, for example, this one has a bunch of electric forces that are acting upon it. And fortunately, the strong nuclear force is much bigger, but since the strong nuclear force acts over very small distances, if that atom gets too big, or if that nucleus gets too big, gets too many protons crammed in there, the strong nuclear force won't be big enough to make it stable, to hold it all together. All right, so unstable nuclei are that way because they're too big. All nuclei with Z bigger than 82 are unstable. Z bigger than 82, that's lead, Pb, are unstable. For A less than 40, I mentioned this already, but for A less than 40, those are smaller nuclei. Uh, so a Z of 20 and less, right? A is the atomic mass, Z is the atomic number. For A less than 40, stable nuclei have about the same number of protons and neutrons. All right, so for example, carbon 12, 6 is stable because it has equal numbers of protons and neutrons. That's not always true, but usually it's about true. So if they have about the same number of protons and neutrons, they'll be stable. Okay, we have a few minutes. I want to show you one of the types of decay. We're going to look at several different types of decay. Um, Actually, no, I don't think we'll. Let me just sort of introduce nuclear radiation and the types of different decay, but then you'll need to read about the types of decay, which we'll get into next time. And when we finish, I'll tell you what section to finish up to. It's not going to be much of a chapter. All right, so we have types of nuclear radiation. Me too, what? Are y'all tired? Ready to go? Stressing? Over this class? No. Listen, read the chapter, you'll be fine. We'll go over next time sort of what to expect for the test, but you're going to see several different types of decay. So when you're reading in the next couple of days, read over those types of decay. All right? And if you don't want to, well, no, you should sweat the quiz because it'll be on the exam. So do sweat the quiz. It'd be nice for you to get another 50, right? Yes. Okay, so the types of nuclear radiation, um, there are three types of decay. Right, when these nuclei get too big, they become unstable, they decay into something that's more stable, usually into another type of atom. So these three types of decay include alpha decay, beta, and gamma decay. And again, I might use the Greek letters, I'll sort of use them interchangeably. Alpha, beta, gamma. All right, alpha, beta, and gamma. In decay, one nucleus is changed. It may become a new element, but might not. We'll see somewhere that doesn't happen. But it usually is changed and may become a new element, usually becomes a new element. We have a couple terms. The parent nucleus is the original nucleus before decay. And the daughter nucleus is after decay. All right, the parent gives birth to the daughter. The first nucleus, the one that's unstable, is the parent nucleus, and then the one after the decay at the end of the reaction is the daughter nucleus. We're going to represent the equation, the decay equation, like this. And we'll get into this next time, how this works. Our element, this is just some unknown element, some whatever. A and Z numbers, our atomic and mass numbers, will give rise to some different element, I'll call it X prime, A prime, Z prime, plus some type of radiation. So that'll be the general idea. It might change a little bit, like sometimes we might, in fact, add some type of radiation here, or some type of particle here, and then go to some new particle. The radiation can be either alpha, beta, or gamma particles. But other types of radiation might occur. But as far as we're concerned right now, we're just going to look at alpha, beta, and gamma. All right, I think that we'll stop there. Let me give you the section. And then next time we'll have the quiz in the beginning, and we'll look at the different types of reactions, and we'll stop after those. Alpha. Yeah, we're going to stop after gamma decay. So in your book, that is We're not going to do the decay chain. Yeah, we're going to stop on page 222. So on page 222, we're going to go up to where it says decay chain. All right, page 222 is the section. We are going to cover the section on gamma decay, but we're not going to cover past that. Read the chapter, read it several times, okay, sort of highlight the main ideas, and you'll be good for the quiz on Thursday. All right. Make sure I'm going to ask you a couple questions about the reactions, the alpha, beta, gamma decay stuff. So learn those now, and then um, about the models, about the atomic notation or the nuclear notation, know how to interpret that. Well, how many neutrons does this have? How many protons does it have? That sort of thing. Any questions, y'all, before you go? No. Have a great day. Don't sweat this too much. Well, do sweat it a little bit, okay?